Okay, so the plan for today is to actually start the next chapter, chapter 4 on graphing. And we're going to start 4.1, basically complete 4.1, and probably get a bit of a start on 4.2 today. And then we'll continue on with 4.2 and 4.3 next class meeting. Super important note, I didn't spell that right. There is a graphing tool supplement posted on Blackboard. So unfortunately, the WebAssign graphing tool, like the native embedded graphing tool that you use to answer some of the graphing questions, there is a little bit of a learning curve to it. A couple of the buttons, it's not 100% clear exactly how to use them, and that's what this supplement kind of walks you through. So I would strongly recommend before using the graphing tool on WebAssign that you go through and just take a glance through that supplement. It's not hard to use. It's just there's a couple of quirks, and once you kind of realize those couple of quirks, then I think it's pretty straightforward. But mainly just a couple of things like, when you click a button that opens a drop-down menu, the menu drops down like over top of the button. So like we're used to, for instance, if I have my button up here and I click it, the thing that drops down is strictly below it. So like, just a few little quirks like that. And one other note is be careful that there are different kind of things related to lines on there. There are kind of line segments that don't extend forever. They just go between 2 points. There are rays that are like one-sided lines that like extend forever in one direction but not in the other direction. And then there are lines that extend forever in both directions. So just make sure that you're using the appropriate one of those. So for our discussions, that's usually going to be the line that extends in both directions. But again, take a look at the supplement and just be a little bit careful when you're using that graphing tool the first couple of times. And I think that, after you've done 2 or 3 problems with it, it'll be pretty smooth sailing. But just some of those little nuances can catch you off guard at the beginning. The the quote of the day is from hedge fund manager turned author / philosopher. I guess he kind of considers himself a philosopher these days, Nassim Taleb. And he wrote a book called The Black Swan, and it was talking about events, particularly in financial type settings, but also just kind of generally in humanity, where we think that we've come up with a model. We're like, okay, yeah, we really understand this. We really know how the world works in this aspect. And then a black swan, so to speak, pops up. A very strange event that hadn't occurred before pops up. It doesn't fit our model. And then all of a sudden we're kind of thrown into chaos. And we're like, wait, I thought my model was great. Maybe it's not so great. So I think a lot of mathematics is used in the applied setting to create models, and we should always be cognizant that our models are not the rules that reality follows, right? If we say F equals ma, physics doesn't follow F equals ma. We've come up with some mathematical structure to model what physics does, but physics is going to do what it does. So just by gathering empirical evidence, just by the scientific process, we can't come up with universal truths. We can, don't get me wrong, it's extremely useful. We can make very good predictions, but there's always an element of modesty that should be, or of humility, I suppose, that should be considered, that we don't have access to the kind of underlying universal truth. We're trying to make better and better models. There's also Isaac Newton, possibly one of the probably one of the like best, in a sense, scientists in history. He kind of described his work as meandering along a beach, and he's looking for shiny pebbles, and he gets all excited when he finds a pebble on the beach that's a little shinier than the one that he's currently holding, and meanwhile there's a vast ocean to be discovered that he's not even seeing. Or Richard Feynman, Nobel laureate physicist, came up with quantum electrodynamics and Feynman diagrams and a lot of other cool things. Actually, not him personally, but his character made a cameo in Oppenheimer. He was the one playing the bongo drums famously. That was a Feynman thing. He talks about there's a really cool interview with him from probably like the 70s or something. This interviewer is just, asking him all kinds of questions. He's giving all kinds of crazy answers, and you can find it on YouTube. It's entertaining to watch. He's a very entertaining kind of guy, not a dry physicist or mathematician like so many of us are. But Feynman talks about, us discovering the process of scientific inquiry and discovery as being like gods are playing chess on a chessboard, and we don't know the rules. We can only see a little corner of the chessboard, and we're trying to extract the rules of the chess game on the basis of our little bit of observation that we see. And we make a rule like, oh, pawns can only move, one step straight forward, or okay, maybe sometimes they can move 2 steps straight forward. And then, oh wait, that pawn moved diagonally to capture. Like, what was that? That was something I haven't seen before. I need to adjust my model for that. So a lot of the utility of mathematics is in constructing models, and models that we apply to the real world to understand things. But we should always just be aware of that even these great scientists see these as models. These aren't, universal truths about our world. They're hopefully things that we can use to make predictions and to make our lives better and to understand things better. But we ought to always take them with a grain of salt. Okay, so moving into 4.1, using the rectangular coordinate system. So the rectangular coordinate system also has another name as an aside, the Cartesian coordinate system, named after the French philosopher René Descartes. Famous, I think, therefore I am, cogito ergo sum. Basically, he was saying, like, how do I even know that I exist? Well, I think, therefore I am. So, roughly speaking. But from the last little bit of his name here, this is also sometimes called the Cartesian coordinate system. So Cartesian coordinate system, rectangular coordinate system. And basically the idea is to construct this. We take a number line. We've seen a number line like this before many times. We take such a number line, and let me see if this will work. I'm not 100% sure that I can make this work, but we'll try to use technology to. Oh, I went the wrong way there. Okay. We make a copy of that number line, we turn it 90 degrees, and now we have 2 copies of the number line. So before we could traverse the number line left and right, and that was in 1 dimension, 1 spatial dimension. But now we can traverse left and right, but we can also traverse up and down. This is in 2 spatial dimensions. So if we were to imagine, let's say we have like a crane hoist up in the top of a warehouse or something, if it's on a single track, we can only lift things up and move them along 1 dimension, forwards or backwards. But if we somehow had it on, one of the hoists on 1 track, and then that hoist was attached to a hoist above it that was on a perpendicular track, we could take that object that it's holding and move it forwards and backwards, but also left or right, or really any direction. We can move it a little forwards and a little right to go diagonally, or so we're now in 2 dimensions, 2 spatial dimensions. We have a up and a down and a left and a right direction. Typically, we call the horizontal axis the x-axis and the vertical axis the y-axis. That's just kind of the standard, the standard where we typically use, x for a variable, or typically use, say, a or something for a constant. But that's not to say that in no situation could you ever call the horizontal axis Y or the horizontal axis Z or something, or but typically we call the horizontal axis X and the vertical axis Y. So that's the default. If we don't have any other context saying otherwise, that's the assumption that we make, is X is the horizontal axis, Y is the vertical axis. We note that the intersection of these two axes, which by the way we call the origin, let me try to get a different color here. This intersection of these two axes gives the name the origin, kind of where all of the positive and negative directions in either horizontal or vertical direction originate, the origin. We note that the cross here splits the two-dimensional like page or your paper or your tablet screen into 4 quadrants called quadrants, because the word quad is associated with 4 things, kind of the same root word as like quarter. So there's an upper right quadrant, an upper left quadrant, a lower left quadrant, and a lower right quadrant. And in fact, if you're in medicine, if you're taking nursing classes or something, you might hear of like, oh, patient had pain in their lower right quadrant. That's kind of like where your appendix is or something. So you might even use that terminology to talk about a person's torso, lower left quadrant, lower right quadrant, things like that. But in this case, we're labeling these as quadrants, and we label them, we notice that there is a positive X side and a negative X side, just like on a number line, right? There's also a positive Y side and a negative Y side in the vertical direction. Again, just like on that second number line, we have a positive side and a negative side. We label the first quadrant. It's the quadrant that's associated with the positive Y and the positive X. That, I suppose, makes sense. Maybe that should be the first quadrant. That's kind of where we'll start, where everything is positive numbers. And then we proceed counterclockwise. So if we go counterclockwise, we're kind of traversing right to left across the top. That brings us to quadrant 2. Continue going counterclockwise, we're traversing up to down on the left side to quadrant 3, and then traversing left to right across the bottom over to quadrant 4. And if we were to keep going, we would end up back in quadrant 1. So we have labeled all the 4 quadrants. So we don't label the quadrants like how we would, maybe read a book, like top left, top right, bottom left, bottom right. Then we'd have kind of quadrants that aren't really contiguous with their neighbors. So like quadrant 3 would be like far away from quadrant 2 in some sense. So there is kind of a rationale for doing it this way. When you get to say maybe trigonometry or something, when there's more relationships with angles relative to these quadrants, some of this starts to make a little more sense why these are defined this way. But here, quadrant 1, upper right, and then we go around counterclockwise for quadrants 2, 3, 4. And in case I didn't say it already, I think we know this terminology probably, but these number lines we now tend to call them axes. So we'll talk about the x-axis and the y-axis. And kind of the idea of these 2 number lines is to allow us to take, say, some arbitrary point in 2 dimensions, maybe it's this one, and to give its location. The same way that I might say the location of Pittsburgh is, so many degrees, what would it be, like north in the latitude, and so many degrees, whatever direction in longitude. And then I can pinpoint where Pittsburgh is. I need to say how far, in a sense, kind of up and down I have to go, say, from the equator to get to Pittsburgh, and then how far, in some sense, left or right from whatever line it is over in England. Is it like Greenwich, England, or something? How far do I have to go left or right from there to get over to Pittsburgh? And then I can say exactly where Pittsburgh is on the globe. Don't take my statement as implying that I think the Earth is flat, but we can roughly think of the Earth as being flat for our local properties. But if I want to go north and south a little bit, or east and west a little bit, that's a similar setup to this Cartesian plane. So I would like to be able to describe locations in this plane, and I'd like to be able to describe them pretty efficiently. So like I mentioned before, is we have a default assumption that the horizontal axis is X and the vertical axis is Y. And under this labeling, if the horizontal is X and the vertical is Y, we can talk about a point in this plane as X comma Y. Now, unfortunately, we kind of draw this, we denote this, what we call an ordered pair, using parentheses and a comma. And unfortunately, that looks the same as interval notation. So recall, if I had 3 less than X less than 4, I'd write that as like the interval 3, 4. So kind of unfortunately, ordered pair notation looks like interval notation. But these are 2 different notations, so not the same. And how do we tell the difference? Well, context. Are we talking about graphing something on a 2-dimensional plane? If we see this notation, then it's an ordered pair representing the location of a point in the plane. Are we talking about a solution to an inequality? Maybe a slightly more complicated inequality than the ones we've seen so far, but in that context, we would say, okay, this is an open interval. This is an interval where I don't want to include the endpoints. But context would tell us which of these 2 the notation is indicating. So if I look, for instance, at 6, 4, what I'm saying is I want to go to the location. I want to go to the point where X equals 6 and Y equals 4. So the X coordinate, or the horizontal coordinate, always comes first. The vertical comes second. It's easy to get that backwards and to kind of forget that. But again, it's one of those things that after you go through and do this, once you plot 10 or 20 points, it becomes a little easier to remember which way it goes. But for right now, maybe write a little note on a piece of paper or post it or something that it's X comma Y, like horizontal comma vertical, and that'll help you keep it straight for the time being. Let me make my screen just a little bigger so I can get a little more of this on here. There we go. I'm trying not to shift things up and down because I'm worried that these points that I drew on here below will get messed up if I shift anything up or down. But I want to plot these points, in particular, starting with 6, 4 on this plane. So what do I do? Well, I want the point on the plane, I want the 2-dimensional location that's associated with the horizontal value of 6 and a vertical value of 4. Or we can think of it kind of like a latitude longitude idea or something like that. Or if I was in the middle of a town that's not, triangular like Pittsburgh, but a town that's more on a rectangular grid layout, I could say I want to go 6 blocks in the horizontal direction. In this case, I would want to go 6 blocks east, and then 4 blocks in the vertical direction north. So I start at the origin where I always start at, and I go 1, 2, 3, 4, 5, 6 over to x equals 6. So I went 6 blocks east from the origin, or 6 blocks to the right. And then I want to turn and go 1, 2, 3, 4 blocks north. This would be our point 6, 4. So we kind of think of starting our point prospectively at 0, 0, adjusting it to get its x coordinate correct, and then adjusting it further to get its y coordinate correct. And if I erase these so that I don't have extraneous points on here, we see if we go to the location x equals 6, y equals 4, I would put a point there, and I might label it as 6, 4. And OneNote just hates letting me draw 4s. There we go. 6, 4 on my graph. I could label -2, 5. If I have a negative number for x, but I know how that works with a one-dimensional number line. If I'm at -2 on my one-dimensional number line, I would be here. So my x direction, my horizontal direction, is going to be 2 units to the left of the origin, indicating -2, or 2 units west, so to speak. And then my y coordinate is +5. So I would go up to +5 from there. And again, I'll just erase this so I don't have extraneous stuff floating around. So this is the point with coordinates, x coordinate -2, y coordinate +5. So we've got these two, -3, 8. If I want -1, -2, -3, going to the left 3, and then going up 8. There's -3, 8. If I have, say, -7, -1, going 7 to the left on the x-axis, or going to the x location -7, and then looking for the y location -1, so going vertically down 1 unit, there's -7, -1. And if I wanted, I guess I didn't write it up here, but if I wanted, say, so we did these two, if I wanted maybe 3, -2, let's say, I would go to 3 on the x-axis, down 2, so looking for that intersection with -2 on the y-axis. This would be 3, -2. So I noticed that points in quadrant 1, those are associated with +x and +y. Points in quadrant 2 are associated with -x and +y. Points in quadrant 3 associated with -x and -y. And in quadrant 4, +x, -y. So each of my x and y can be positive or negative, and these are the 4 possible pairings. If I wanted to look at, say, 6, 6, I see that's 2 positive numbers. That's going to be in quadrant 1. So if I go over to 6 and I go up to 6, there's 6, 6 in quadrant 1, as I expect, with 2 positive numbers. Are there any questions so far? Okay, so what about these couple of maybe special cases, something like, say, 8 comma 0? Well, if I can think of this kind of either way. I can think of starting at the origin, starting at 0, 0, going to the right 8 units, and then moving vertically 0 units, so just staying here. Or I can think of going to location 8 on the x-axis, and then moving vertically from there to go to location 0 on the y-axis. But remember, the origin is where those zeros of both axes meet. So 0 on the y-axis is really just indicating that the point is on the x-axis. So 8 comma 0 would be this point here. It lays directly on the x-axis. The point, say, 0 comma 1 similarly says start at the origin, don't move at all horizontally left or right, move 0 units left or right. How should we move vertically? We should move 1 unit vertically. To bring us to 0 comma 1. Or again, we could also think of this as saying, where's the location 0 on the x-axis? That's actually the y-axis. And then we want to move along that y-axis, that vertical axis, till we get to the location 1 vertically. That moves us 1 up from the origin. And then, of course, the point 0, 0, which point in the 2D plane is location 0 on the x-axis and also 0 on the y-axis? Or if we started at the origin and we don't move it all in the horizontal direction, then don't move it all either in the vertical direction. 0, 0 is just the origin. Okay, so let's take a minute and practice this. So plot each of these following points on this Cartesian plane below, or this rectangular coordinate plane. So I'll give you maybe 3 or 4 minutes. It might take you a minute to kind of write down on your notebook paper, write out a plane, and then plot these points. Try to do it, reasonably accurately, but it doesn't have to be like, ruler level straight lines, or like, measuring tape, precise increments of 1, 2, 3, 4. It doesn't have to be that perfect. This is more of a diagram or schematic than intended to be something like a perfect, engineering drawing type thing. So take maybe three minutes or so, work through this problem, and then we'll come back and discuss it. Okay, it's about 3 minutes, so let's work through this. So I'll go little more quickly than I did last time. 3 comma 2, we know this is related to x equals 3, y equals 2. Going to 3 on the x-axis, 2 on the y-axis. That point's 3 comma 2. 4 comma negative 1. So I want location 4 on the x-axis, negative 1, so 1 down. On the y-axis, there's 4 negative 1. Negative 5 comma 7. Going to negative 5 on the x-axis, so left 5 units. Then up 7. And negative 3 comma negative 3. 3 units to the left, 3 units down. That's this point. 0 comma 2, so x location 0 says that we're going to be right on the y-axis. And I want to be at y coordinate or y position 2. So this is 0 comma 2 for that point. 6 0 is 6 units over on the x-axis, 0 up or down, location 0 on the y-axis. And 0 0, like we saw last time, is our origin right here at the intersection of the two axes. Any questions on this? Okay, so let's come down to the next example. And here again, we have our Cartesian plane with an x and a y axis. And in this case, we have 5 points drawn on the coordinate plane. And we want to go the other direction. So given a point on the coordinate plane, can we identify its location in ordered pair notation? I want to give an ordered pair for each of these. And I'm actually just going to write it directly on the graph. Maybe I won't use blue because the background lines are, but maybe I'll try green. So if I take this kind of, this one that's at the very top up here, this one, I want to give it an ordered pair. So I need to find its x location and its y location. I see if I go straight down to the x-axis, this is at location x equals negative 5. Let me erase these dashes. I just did that for kind of scratch work, but my x coordinate is going to be negative 5. And then I see if I go straight over to the y-axis, that's y location, positive 7. I know this is in quadrant 2 where I have a negative x and a positive y, so that makes sense with the quadrant that I know that I'm in. If I look at this point over here, a little lower and to the right in the first quadrant, I see its x position is 3, its y position is 3. It's going to be at location 3 comma 3. Going back to the left, I see this point over here is at x position negative 7, y position positive 2. Coming down to the third quadrant, x position negative 1, y position negative 5. Again, meshing with what I know about the third quadrant, that both coordinates should be negative. Oh, And then lastly, I don't know why it did that, but right. Lastly, in the fourth quadrant over here, X position 6 and Y position -2. So at this point, at least, if I mean, my drawing is not perfect, so we're kind of picking the closest integer point. You can have fractional points. We could have, a point, say here. We could have a point like X location 4.5, Y location -1. There's nothing wrong with that. The same way that on a one-dimensional number line, we could have fractional coordinates. That's fine. We haven't really talked about that much yet. We're sticking to maybe the integer points here. So if I'm off a tiny bit or something on a coordinate, we'll just call it the nearest integer point. This is a little bit like in geometry, how we might draw a rectangle or draw a triangle, but we don't intend for it to be perfectly dimensionally accurate, right? If I draw a triangle that I'm going to try to use to solve some problem about a ladder leaning against the house or something, I'm not at the outset or even afterwards trying to draw that triangle super accurately. If it's a 3, 4, 5 triangle, I'm not trying to draw it so that the proportions are exactly 3, 4, 5 between the sides. It's more of a diagram. A coordinate plane kind of stands somewhere in the middle there. It's still quite a bit of a diagram. It's not meant to be extremely accurate. It's a little bit more accurate than something like drawing a triangle or rectangle, because we have this grid that kind of that gives us a little bit more structure to work with. But again, we're thinking of this as a not completely accurate graphical representation. So it's just got to be accurate enough to be helpful, to be beneficial to us. Okay, so let's come over here and take these 4 points, one in each quadrant, go through and label them. We'll take maybe just a minute or so. I think in this direction, things go a little more quickly, and also you don't need to write down a coordinate plane. So we'll take about a minute, label each of these 4 points, and then we'll discuss them. Okay, it's been about a minute. So let's just start in quadrant 1 and work our way around the quadrants. So up here in quadrant 1 on the top right, I see this point has X location 3, X position 3, Y position 8. So this is going to be 3, 8. The quadrant 2 point on the top left, this has X position -8, Y position +8. So this will be at -8, 8. The quadrant 3 point on the bottom left, X position -6, Y position -2. And quadrant 4, bottom right, X is 2, Y is -2. That point is a position 2, -2. Any questions so far? I think going this direction is a little easier than going the other direction. Okay, so now let's take a look at equations, particularly linear equations, in two variables. The standard form of a linear equation looks like this: ax plus by equals c, where a, b, and c are some constant real numbers, and x and y are variables. So for instance, we might have something like 3x plus 2y equals 4, or negative 5x plus 3y equals negative 2. Anything kind of in this general form, we would call standard form. We can have linear equations in other forms. We could have a linear equation like 3 times x minus 7 plus 4 times y minus 2 equals 7y minus x or something. I mean, you could say, okay, this is a linear equation in two variables. It still satisfies the constraints of, we have two variables, x and y, and each one of them is linear in the sense that it's not like square root of x, it's not like x squared or something like that. This is still a linear equation. But it's not in standard form. Often, we like to put certain types of equations in standard form because a lot of times we can extract information kind of more directly from that standard form or more easily from the standard form than from an arbitrary form. So, for instance, solving quadratic equations in Math 108 using the quadratic formula, instead of having to go through and do factoring and do all of this extra work, you can take your quadratic equation, plug it directly into a formula. But to use that formula, you need to kind of know essentially what the a, b, and c are in kind of the equivalent context. So we would need to have a standard form where we can pluck out these different numbers and know which number should be plugged in which places in the formula. It's a little bit similar here. We like to write things in standard form because it's a more recognizable notation. Any linear equation can be written in standard form, right? I could imagine over here, I'm not going to go through all the steps, but like this is a pretty crazy looking form. What could I do? Well, I could multiply out all the parentheses and combine like terms. On the left side, I would have an x term, a y term, and a constant term. On the right side, I have an x term and a y term. I can move the constant term to the right by adding or subtracting. I could move the x and y terms on the right side over to the left, again, by adding or subtracting, combine like terms, and I would have something that's in the standard form. So I can get any linear equation into this standard form, ax plus by equals c, and sometimes I want to do that. So for example, consider this linear equation. If you wanted a challenge, you could try to convert this linear equation into standard form, but just to show the process, if we want to convert this following linear equation into standard form, y equals 7x minus 4. This is another common form of the equation that's used more in maybe like Math 108. This would be called the slope-intercept form. But what if I wanted to convert this into standard form for what we're going to be doing in the next couple sections? Well, I see I have a y term on the left side. I have a constant term on the right side. But I need to move this x term. This x term, to be in standard form, belongs on the left side alongside the y term. So I would just subtract 7x from both sides. And I'm a little cramped here, but that gets rid of the 7x on the right side, leaving me with just the constant term negative 4 on the right side. And on the left side, I have negative 7x plus y. So I have the coefficient of x is a is -7. The coefficient of y, we don't see it explicitly written, but we know that when we don't see a number in front of a variable, that just means it's 1 times that variable. And then c is -4. This could be helpful to us in the future if we want to work with the standard form of linear equations. So now let's look at solutions to linear equations in 2 variables. So first, remember what it means to be a solution to a linear equation in 1 variable. If I had, say, 5x minus 2 equals 3. The question that I'm asking is, what value, or perhaps values, could I substitute in for the variable x that will yield an equation that will yield a claim that is true? If I substitute in x equals 0, is it true that 5 times 0 minus 2 equals 3? No. So x equals 0 is not a solution. But if I substitute in x equals 1, is it true that 5 times 1 minus 2 is equal to 3? That's 5 minus 2, that is 3. I have 3 on the left, 3 on the right. That is correct. X equals 1 is a solution, and as we discussed before, it's the only solution to this linear equation in 1 variable. What does it mean for something to be a solution to a linear equation in 2 variables? It means I make a choice for x. I make a choice for y. Is it true that when I plug in 3 for x and 10 for y, I get a correct equation? Well, this gives me, 16 equals 10. That's not true. This is not a solution. But does that mean that, like, x is never allowed to be 3? What about if I used x equals 3, but maybe I use a different value for y? Well, what would my claim be then? So this was one part, this is a different problem. What if I instead tried plugging in x equals 3 and y equals 16? Is it true that 16 is equal to 5 times 3 plus 1? Is it true that 16 is equal to 15 plus 1 is 16? That is true. This is a solution. Do I think this is the only solution? Well, what if I, for instance, plugged in x equals 0? I might be interested in knowing, I see that, for this choice of x, for 3, some y's don't work and some y's do work. I might be interested in knowing, for a specific choice of x, is there any y that works? And if so, what is it? What if I plug in x equals 0? What is the y, or possibly multiple y's, or possibly no answer, but what is the value of y that I would have to choose to plug in here to make this a valid equation. I see I can simplify the right-hand side. I get a valid equation if and only if y equals 1. So if I make a choice for the value of one variable, if I choose a number to plug in for x, like x equals 7, what that yields in the other variable is a one variable linear equation that I can solve for that other variable. Likewise, if I had chosen y equals 10, and I want to know if I plug in y equals 10, what's the value of x that would create a correct claim, a correct statement. So I want it to be true that 10 equals 5x plus 1. And again, note that this is a linear equation in one variable, and I know how to solve those. I subtract 1 from both sides. I divide by 5. In this case, I got a value for x that's not a whole number. It's not a nice round integer. But that's perfectly okay. There's nothing saying that these always have to be integers. But something that I realize is that x equals 3, y equals 16 is a solution to this equation. X equals 0, y equals 1 is a solution. This one I kind of constructed. X equals 9/5, y equals 10 is another solution. And it kind of feels like for most of these problems, for whatever x I pick, whether I pick x to be -10 or +100 or 17.5, if I pick an x, I can find a y to go along with it that yields a solution. It seems like that's going to happen, at least, most of the time. It seems like that's going to happen. That if I pick a certain value for x, I can find a y to go along with it to make a solution. Or if I pick a certain y, I can find an x to go along with it to make a solution. So it seems like I'm going to have lots of solutions, lots of ordered pairs, x and y, each of which represents a solution. Now be very careful, just because there are lots of solutions doesn't mean that everything is a solution. But it does seem like if I make a choice for x, I can find a y to go along with it that makes a solution. And if I make a choice for y, I could find an x to go along with it that makes a solution. And then I could think of these as ordered pairs, and you can probably guess that we're going to tie this back to graphing. Once we write things in ordered pairs, we might want to make a pictorial representation of what these solutions look like on the picture. Okay, so let's come up here and look at this table. And in this table, I have, whoops, I don't know how that happened. Thank God for undo. In this table, I have one column that represents some different x's that I would like to plug in, and another column is with their associated y's and associated y values, and then a third column where I'll just write out the ordered pair. So for instance, if I wanted to plug in x equals 1, and I wanted to figure out what value of y will yield a correct equation. Well, if I plug in x equals 1, I see that I had better choose y equals 6, or else I don't have a solution. And I could write this as the ordered pair x comma y, 1 comma 6. X equals 1, y equals 6 does represent a solution to this equation, y equals 5x plus 1. Okay, different problem. If I want y equals 16, what value do I have to plug in for x to make this equals a true statement? Let me give myself a little more room here. If I want y to be 16, that means I have to have 16 equals 5x plus 1. This one requires a little bit more algebra to solve. I subtract 1 off both sides. I divide by 5. So if y is 16, x had better be 3. That's the only way I'm getting a solution when y is 16. So 3 comma 16 is another ordered pair that also represents a solution to this equation, y equals 5x plus 1. Loosely speaking, we can also think of like variables are things that we get to choose. So if I just give you a Cartesian plane and say like, find a point on this plane, you can pick the x value however you want, and you can pick the y value however you want. You have 2 degrees of freedom. You can move horizontally and you can move vertically. Those are 2 kind of independent ways that you can move that don't affect one another. Those are 2 degrees of freedom. Saying, I want this statement to be true, y equals 5x plus 1. I want this relationship between those 2 variables or those 2 degrees of freedom to be true. Puts forward one constraint. And quite often, one constraint takes away 1 degree of freedom. So in other words, I have 1 degree of freedom. I can pick, say, x any way that I want, but once I pick x, that sets in stone what y is. Or maybe in a different context, I could pick y, but once I pick y, I've burned my 1 degree of freedom. Now x is determined. That's a little bit more abstract, but that's a kind of another way to think about this. And then lastly, if I have x equals 0, what's the y value associated with x equals 0 that gives me a correct equation? Maybe I'll try to squeeze that in here. If x is 0, then y equals 5 times 0 plus 1. Oh, we actually already did that one. Y equals 1. So if I have x equals 0, I had better also choose y to be 1. That's the only way that I'm going to get a solution to the equation. So 0 comma 1 would be another ordered pair that represents a solution. We see that there are lots of ordered pairs, and of course, even more. I could have picked more different choices for x and more different choices for y, and gotten more different ordered pairs that represent solutions. Let's do one more of these, and then we'll work on a couple of them for practice. So here I have another linear equation. This one is in standard form. The last one was not in standard form. And again, I want to fill in this table. So I know that for these kinds of linear equations, where I have a linear equation and 2 variables, once I choose a value for one of the variables, that essentially determines the value for the other variable. There are some niche cases where we have to take a little more care in statements like that, but most of the time, once we determine one variable, that determines the value for the other. So if x is 0, that means that 3y plus 6 times 0 has to equal 18. Now I can solve for y. This bit, 6 times 0 is just 0. Divide both sides by 3. So when x equals 0, y has to be 6 to satisfy this equation. And our ordered pair, 0, 6. If I want to know what value of x is associated with y equals 2, I plug in y equals 2, and I now have a linear equation in one variable for x. And I can solve this. What are my equation solving steps? I simplify. This one you might even be able to guess the answer to, but let's go through the steps. I see that if y is 2, x had better be 2 in order to satisfy this equation. And lastly, if y is 0, what does x have to be? Well, 3 times 0 is just 0. When y is 0, x has got to be 3, so that 6 times 3 equals 18. So 3 comma 0 is another solution to this equation. And again, these aren't like the only 3 solutions. We could have picked a bunch more values for x or a bunch more values for y, but this is a list of some solutions. It's a sampling of solutions to this equation. Any questions so far? Okay, so I'm going to put these next. I think I'll actually just put all 3 questions on the screen so you can work through them. Small problem, convert this linear equation into standard form. Remember, which is ax plus by equals c. And then these two, fill in these 2 tables for these 2 equations. So let's take about, let's say about 5 minutes for all of this, and then we'll come back and discuss them. So take about 5 minutes, work through these 3 problems, and then we'll come back. Okay, it's about 5 minutes. So I worked through the first one up here, this problem converting into standard form. We want to convert into the form ax plus by equals c. We can get the x term over on the y term side. We could just move the y term also, I suppose. We could just subtract y from both sides. We could do it that way as well. But I could get the x term over on the y term side by subtracting 2/3 x to get y minus 2/3 x plus 5 equals 0. And then I could get the constant term on the other side by subtracting 5. So I get y minus 2/3 x equals -5. Or I suppose if I wanted to be really strict, I could write it -2/3 x plus y equals -5. Something that you may have done is you may have taken a different approach. And like I said, what if I subtracted y from both sides? Or what if I had gotten 2/3 x minus y equals 5? Is this wrong somehow? Well, no, it would just be a slightly different version of the standard form, right? If I multiply both sides by -1, which I could definitely do, I would get -2/3 x plus y equals -5. That's what I have over here. So there can be these kind of minor nuances. If we wanted to be really particular, maybe we would say, okay, standard form is like ax plus by equals c, where a is positive or something. That would give us a completely well-defined problem. But for now, I think if we get either of these, that will satisfy anything that we need for right now. Okay, so if we want to fill in the table for y equals 3x minus 1, when x equals 1, we see that y has to be 5. Pretty simple calculation there. When y is 14, we have 14 equals 3x minus 1, and we solve that for x to figure out when y is 14, what's the associated value for x that we need. And that turns out to be x equals 5. And when y is 0, what value of x do we need? We need to solve the linear equation 0 equals 3x minus 1, or we get x equals 1/3. Again, these coordinates, these solutions, don't have to be whole numbers. They can be fractions or decimals. We've been dealing mostly with whole numbers so far, but we certainly could have a fractional answer or a fractional point on the Cartesian plane. And then this last one, let's work through that together. So I'll go through and delete my question marks here. So for x equals 0, we have 6y minus 2 times 0 equals 12. This is 0. 6y equals 12. Divide through by 6, and we get y equals 2. For y equals 3, I have 6 times 3 minus 2x equals 12, and I need to figure out what the associated value of x is to y equals 3. So I have 18 minus 2x equals 12. If I subtract 18 from both sides, -2x equals -6. I divide through by -2. Remember, this is not an inequality. This is just an equals. So we don't have to worry about flipping direction or anything like that. Divide through by -2, and I get x equals 3. Does that make sense? 6 times 3 is 18, minus 2 times 3 is 6, 18 minus 6 is 12. That does make sense. So another ordered pair that would represent a solution to this equation in two variables is 3, 3. And then lastly, y equals 0. 6 times 0 minus 2 times, 2x equals 12. And what is x? Well, this is 0. Negative 2 times y equals 12. That's going to be negative 6. So I have x equals negative 6, y equals 0. Or negative 6 comma 0 is another solution for this. And just a reminder that in both of these tables, this is just a sampling of solutions. I could have picked lots more choices for x, lots more choices for y, and got lots more solutions. In fact, I could have picked infinitely many, choices for x and got infinitely many solutions. Right, x equals 0, 1, 2, 3, 4, up as high as you can go, or the negative numbers, or the fractions, or decimals, or okay, so for the last little bit of class, let's look at a couple related problems. So here we're given a little less direction. Find 3 solutions for this equation. In other words, pick whatever 3 different values for x and find their associated values for y, or 3 different values for y, or some combination of the two. Now, one thing, if we look ahead a little bit, if we think about where we eventually want to go with this, let me come up here, where I might eventually want to go with this is, say, plotting these solutions on a graph. Some solutions are easy to plot, some are a little harder to plot, some are really annoying to plot. Solutions that are like, well, I don't have any on this page, but solutions that are, say, fractional solutions, where one of the coordinates is a fraction, those are probably going to be kind of annoying to try to plot on my graph. Solutions that are at integer points inside one of the quadrants probably are not going to be too bad to plot. But probably the easiest solutions to plot are the ones on the axes. Even if it's a fractional solution on the axis, that's pretty easy to find. So for instance, 3, 0, one of my solutions here, is pretty easy to plot. Or 0, 6 is also pretty easy to plot. Two, 2 isn't too bad. Looking ahead a little bit, and I'm just kind of introducing this idea. We're not going fully into this, but to strategize for how we might want to pick solutions, I actually might notice that it so happens that these 3 points fall in a straight line. And this is kind of special, right? Like, if I just put 2 points always fall in a straight line. But if I have 2 points here already, they kind of determine the straight line. Oops. The straight line that goes through them. If I have a third point, if I just pick it randomly, it's probably not going to be collinear. It's probably not going to be on that same line. So to have a third point that is on that same line is kind of special. We call these linear equations, and you might have thought to yourself, that's kind of a strange name to give them. Why call them linear equations just because they have this form? They're called linear equations because when we plot these collections of solutions on the 2-dimensional Cartesian plane, the result is a straight line. I could imagine curves like, say, for instance, speed versus miles per gallon or something like that, where we would get, say, solutions or data points that do not fall in a straight line. If you're going really fast, your car is not super efficient at high RPMs and you're encountering a lot of air resistance that you're pushing against, you get low miles per gallon. If you're going really slow, your car is spending gas just to stay running while it's sitting still at a stoplight. You're not getting good mileage. But if you're going, 45, 55, 60, something like that on the highway, you're getting a pretty good speed. You're moving forward at a pretty quick speed, but you haven't really hit a ton of air resistance yet to push you back down. So why do we call these linear equations? Well, because when we get these collections of ordered pairs that represent solutions to the equation and we graph them, we get a straight line. Why am I usually finding 3 solutions? Because I would like to have 2 solutions to establish the line and a third solution to act as a check. When I plot that third solution, I can make sure that these 3 points are collinear, that they all lie roughly on a straight line. And that gives me an indication that I have found the correct line, that I didn't make some algebra or arithmetic mistake on one or another of these solutions. So when I find 3 solutions down here, like looking ahead a little bit, I would like to find solutions that aren't super difficult to find. I don't want to pick x equals like 17,432,324. That's going to be super annoying to deal with algebraically. It's also not going to be a very amenable to graphing. So I'd like to find solutions or search for solutions that are easy to solve the algebra and that are easy to plot. 2 good choices are picking x equals 0 and y equals 0. Our 2 points that are on the axes. Now, there are some special cases where this doesn't quite work out, but most of the time this is going to work out just fine. So let's start with these 2. So x equals 0. Then y is going to be -2 times 0 plus 8. Y is just 8. This yields the ordered pair 0, 8, representing a solution to this equation. For y equals 0, I get 0 equals -2x plus 8. I could say add 2x onto both sides to get 2x equals 8. I could divide by 2 to get x equals 4. So when y equals 0, x must be 4. And now I want to have a little bit of foresight. I want to say, okay, I want to choose my next either x or y, maybe to give myself a whole number answer for the other one, or an integer answer for the other one. So if I pick a number like, say, x equals 1, I think that's going to work out pretty well, right? I'm just going to get y equals 8 minus 2. If I pick, say, y equals 1, this is going to be kind of annoying to deal with. 1 equals -2x plus 8. What am I going to get? Like -2x equals -7. X is going to be like 7 halves. That's kind of a pain to deal with. But if I look ahead, I say, okay, if I do x equals x equals +1, is that going to give me something pretty easy to solve, a pretty nice number? Yeah, I think it will. Y equals -2 times 1 plus 8. Y equals 6. That seems like a number or an ordered pair that would be nice to plot. I have so much freedom here that, in a sense, it can be a little daunting. It's like, oh, geez, how do I decide which 3 ordered pairs I want to go after? I have infinitely many of them to pick from. Which ones should I try to pick? But I think this gives a little structure. We want to pick x equals 0, figure out what y is, y equals 0, figure out what x is. And then we want to pick a third choice that, in a sense, is easy to do the algebra and is easy to do the plotting on the coordinate plane. So these three, 0, 8, there's 0, 8, 4, 0, and 1, 6. They're going to look something like that. And I can see, again, looking ahead, we haven't talked about drawing these lines, but we can see that we do have a straight line that seems to roughly go through them, through all 3 points. Now, you might have chosen a different third point. You might have chosen, say, 2, 4 or 3, 2. That's perfectly fine. You know, if you did choose like say y equals 1 and got a fraction out, what did I say it was, like x equals 7/2 or something, you know, I would probably recommend just scratching that one and trying a different one. You know, for a problem like this, if you had this question, say, on an exam, and you get that solution, just go with that solution and be done with it and then move on. But, you know, if our goal is to draw a line eventually, to kind of graph the points and draw a line through them, we might want to kind of engineer things a little bit so that we have points that are easier to place. And this is especially true, this is very true graphing by hand. It's also very true when we're, say, dealing with WebAssign tools, right? I don't want to try to figure out how to get WebAssign to recognize, like, you know, 1 2/3, 7/16 or something. Like, I don't want to try to plot that point on WebAssign's graphing tool. That's going to be annoying. And that's equally true with plotting it by hand on a piece of paper. Like, that's just going to be a hassle. So I want to engineer things a little bit. I want to think ahead a little bit and say, okay, what choice for either x or y is going to give me a pretty nice ordered pair? You know, maybe whole numbers, integers, something like that for my third point. Okay, let's look at this one really quickly. We'll go more quickly through this one than the last one. And then we'll do a couple of practice problems. So again, I'll start by just finding my points on my axes. So when x equals 0, I have 2y minus 4 times 0 equals 15, or y equals 15/2. And here I've got to make a little bit of a judgment call. Is the benefit of having a point on the axis, does that sufficiently offset the annoyance of having to find 15/2? You know, maybe, maybe not, but here we'll stick with it. Similarly with y equals 0, 2y is 2 times 0 minus 4x equals 15. And same question here, right? I get negative 15/4. Does the benefit of having a point that's, in this case, on the x-axis, that makes the location a little easier to find, does that offset having a fraction that I have to locate? Again, maybe, maybe not. But for now, we'll stick with it. And now I have to find another choice. I see that I'm not going to have a particularly nice integer solution, right? My left side, if I pick x and y being whole numbers, being integers, my left side is always going to be even, my right side is odd. That's not going to work out so nice. So this problem is just kind of a little more fundamentally a little less of a nice problem than the last one. So maybe I'll pick like, I don't know, say x equals 1, mainly because x equals 1 isn't going to give me super big numbers or anything like that to deal with. And I think this won't be terrible to do the algebra for. So I get 2y minus 4 equals 15. Add 4 to both sides, 2y equals 19. Divide by 2, y equals 19 halves. Again, not a super nice answer. But like I said, with kind of the evenness versus the oddness of the two sides, it's going to be pretty tough for me to find a nice answer in a problem like this. So sometimes it's just, we got to work with what we got. But I can still find an ordered pair, right? These aren't the nicest looking ordered pairs in the world because of that even odd mismatch, but these are still solutions. Okay, and for the last, let's take 3 minutes until 10:07 and work through these two problems very similar to the last ones. We'll come back and we'll find the solutions on the axes and one more solution in 3 minutes. Okay, so for both of these, I'll start by finding the solutions that are on one or the other axis. So when x equals 0 or when y equals 0. Up here, the First one wasn't bad, 0, -7 being the solution on the y-axis. The solution on the x-axis, a little messier, 7/5, 0. And then lots of options for the third one. I decided to use x equals 1. That seemed like it wasn't too bad to do the algebra and the arithmetic. That gave me y equals -2. So an ordered pair 1, -2. But you could have used, lots of other choices for x and got pretty reasonable, algebra and arithmetic out as well. And for the next one, the solution associated with x equals 0 was y equals 8/3. Just plugging 0 in here and we get 3y equals 8. This solution associated with y equals 0 is just x equals 8. So 8, 0 for that ordered pair. And here, if I look at this, I know that I want to pick an x and a y to make 3 times y plus x equals 8. Maybe if I pick y equals 2 to make this term even, then I have 6 plus x equals 8. Seems like x equals 2, right? That would give me a pretty good ordered pair that shouldn't be too hard to plot. So that would be, one way to go about it. I noticed the 3y is an odd number and the 8 on the right is an even. If I can maybe make that term even by substituting in an even number for y, maybe that will help, right? So I can use a lot of these things I know about arithmetic for how even and odd numbers and so on work to help me out. But again, it's not absolutely crucial in a problem like this to get a number that's easy to plot if we're just looking for a third solution.